Let's have our fifth talk of the first session of the afternoon by David Evangelista da Silveira Jr. from KAUST University, and he's going to talk about stationary mean-field games with congestion.
So, thank you, Vigale, for introducing me, and thank all the organizers for the opportunity to talk at such important conference. And actually, for me, it's a great pleasure to be at this site for the first time. And, well, I will talk a little bit about some mean-field games models. And mean-field games was introduced by Lazare and Lyons around 2006. And roughly speaking, mean-field games are systems of two partial differential equations. The first equation is a Hamilton-Jacob equation that gives some optimal control from the system, the agents, that we always assume that they're rational. And the second equation is usually a transport of density equation. And it's usually actually a Fokker-Planck equation that from the probabilistic point of view, we can think about the random process that gives the dynamics of the agent. And from the infinitesimal generator of that stochastic equation, we can arrive at the Fokker-Planck equation. So both equations are coupled by control term that gives from the Hamilton-Jacob equation. And to have a little bit of the idea that which model we are doing or which situation, just a pictorial thing that we have in mind. For example, suppose we are all at the beach, walking around, and there's an ice cream seller, and all those people walking around are just trying to reach the ice cream seller just to buy the ice cream. So, for example, I think here at Copacabana it would be usually tea with lemon because it's usually different. Yeah, and then what can happen is a situation that with a lot of people just trying to reach a same point, what happens is some crowd motion, and usually the mean-field games it's interesting because it can capture such problem, and we can encode this information on this type of mean-field games that we call mean-field games with congestion. And in this talk, we will speak a little bit about some of the previous development from Lyons in 2011, and give some recent development from Gomes-Mitake and Gomes-Voskayan in 2014 and earlier this year. And the idea is to finish with some a priori estimate that we are developing to show the existence of a marginalized way of the stationary mean-field games, which generalize the previous models. So the first model was introduced by Lyons. It is usually Fokker-Planck, actually a viscous Hamilton-Jacob equation, coupled with the Fokker-Planck, and with some suitable condition on the initial conditions. He showed that there exists uniqueness. Actually, we have existence of smooth solution, and actually he proves from a large class of equations, not only this one, by using monotonicity techniques. And well, we can think, but he doesn't show the existence of solution of this type, existence of smooth solution. Consider the stationary problem of this one. We have Gomes and Mitake showed the existence of the solution of this two equation. It's almost pretty much the same equation, but in the stationary case. They showed also a couple of a priori estimates that encode some information about the term 1 over 2m raised to the power alpha. And that is the most problem that we have in this kind of system, because we must avoid zero solution. We have to avoid the orange. And then in this direction, they developed some a priori estimate to the term 1 over m, and also some estimates to the gradient of u squared over m to the alpha, which gives some information about the Hamiltonian of the system, which gives by these two terms. So this is the a priori estimate that they developed. 1 over alpha is bounded in L infinite, and also they showed the a priori estimate for u and m, which is should be the solution of the system, the unknown variable. and the noun functions actually. And the technique to use to prove this kind of result is first we show that the result holds for W1 infinite, and then by a bootstrap argument we can show that for any integer k, the result holds. So there exists some constant c that depends on the vector field b and the potential function and the term k, that is the regularity of the function. So to give an idea, we want to generalize this type of Hamiltonian, and then we just it's a work in progress by Gomes and Mitake, just considering a general Hamiltonian, just divided by the term m to the alpha, which actually gives this is the responsible term to the congestion. And then they showed it's a little bit different, the techniques here, because we don't have estimates, for example, for u and L infinite, because we have some problem here because we don't have explicit form for the Hamiltonian. And then, but they showed that a priori we have some L1 norm, and also that considering this equation, we have something related here to this one. So we have no explicit condition on this Hamiltonian, but we have some bounds on this term. And which is nice because they used both results to show the existence of solution of this type of problem. So one idea to generalize this model, actually this one, we can think about what should happen if we plug this m to the alpha inside the gradient of u and plug m alpha outside also. It's actually a normalization term for the Hamiltonian. And early this year, Gomes and Voskayan showed that this result holds, actually they showed the existence of a smooth solution, but for small terminal times. For example, here we have the capital T is a short time solution, not for large time T. And the problem that we are interested that we will mention now is consider this problem, but in the stationary case, that would be like putting this term t to the infinite, and is considering the derivative on m on u. So a typical Hamiltonian that we have in mind is this one. So the term b, the vector field b, acts as penalizing some directions. Just because, for example, if you have one ice cream seller and a lot of people just trying to read what happens is congestion, then we must avoid that direction, and the actions that penalize this direction is the term b. And we are dealing with the subquadratic case, which is this power gamma. It's between 1 and 2. And as I mentioned before, they showed that for this subquadratic case and this time-dependent problem, they show that there exists a smooth solution for small terminal times and subquadratic Hamiltonian. So the problem that we are developing at this moment, as we started a couple of months ago, is actually this almost the same, but we have some difference because we must avoid zero solution in this equation. So because otherwise we will blow up the first equation, and we arrived at some couple of a priori estimates for this problem, and which are we must have some hypotheses on the Hamiltonian, because and we have these three hypotheses, which are natural because. For example, if we consider h equals to p squared over 2, we arrive at the previous case. And if we consider p squared over 2, which is the previous case, all those assumptions are satisfied. And so it's a natural thing to do, just some working with some hypotheses on h, the Hamiltonian. So a couple of priori estimates that we have by now is we have already that u is bound non-L infinite, And m, which is the total mass of the system, is equal to 1. It's also a bounded quantity. And this second proposition is a little bit, it seems like the proposition that we have here. We have some control of the gradient of u at some power related to alpha, which is related to the Hamiltonian, which is given by this term. So, and this is a nice estimate because here we have some, we can treat this term by some couple of polynomial estimates also. And we have also this a priori estimate for this equation. And this is it's a nice term because here we have some controls for the entropy that's related only by the dp from the derivative of the Hamiltonian and the term m. And actually, we have a couple of other assumptions that can be treat this term. And in all those, just mention that all those a priori estimates are in the same direction that to show the existence of solution and some regularity a priori that they showed in the previous work. And also, we have also this estimate, and the objective here, the main objective is that we are developing at this moment is to show that some iterative way to deal with this m to alpha plus 1 here, and related to LP and L1 here. And this is a recent technique to use to obtain some polynomial estimates together with some embedding theorems for sublevel space to further show the existence of solution of this kind of problems. So that is the recent work that we are developing, and actually mean-field games treats a lot of class of problems, even in the case of pedestrian or traffic jams, and also for financial markets. And there are a lot of application. The techniques are different from the problem to the other, from one to the other, but it's usually, the direction is usually the same. This use two equation and arrive at some, and the idea is first show existence and everything. That was the most thing that we're doing at this point, and that's. Oh. Thank you.